So now we're going to continue our discussion of the arithmetic operations with division. Again, as with all the other operations, we're going to start with a clear, precise definition of division. Division is the inverse of multiplication, and what we mean by that is that, for example, the answer to the problem 20 divided by 4 is the same number that multiplies by 4 to give us 20. Now, the fact that multiplication satisfies the commutative property, as we saw earlier, gives us two equivalent number sentences to our original number sentence 20 divided by 4 equals blank. 20 divided by 4 equals blank can be interpreted as 4 times blank equals 20, or blank times 4 equals 20. And it turns out that, just like with subtraction, there are multiple interpretations of division. That is, there are multiple kind of real-world situations that both reduce to to division, and these number sentences are going to show us where those interpretations come from. So if we start with the number sentence 4 times blank equals 20, which again we know is equivalent to 20 divided by 4, then if we think about the set model of multiplication that we talked about in our previous clip, 4 times blank can be interpreted as 4 groups of some number. So in this number sentence, we have that 4 groups of some number is equal to 20. And we could represent that pictorially with a bar diagram like this one. So our entire bar is 20. We've got 4 equal pieces, and the answer to the question is what makes up each piece, or what is the size of each piece. Okay? So we could interpret this as just as a question, as 20 is 4 of what, or 20 is 4 of what number? That is the question that's being asked by this diagram. Okay? This interpretation has a name, and it is called partitive division. And an easy way to remember the interpretation is just that partitive division is the interpretation in which we know the number of parts that make up the whole. In this case, 20 is the whole. We know that we're splitting 20 into 4 equal parts, and hence we call it partitive division. Now, on the other hand, 4 times blank is equivalent to blank times 4 by the commutative property of multiplication. So we could also interpret our original division problem, 20 divided by 4, as follows. Blank times 4 equals 20. And again, if we go back to our set model of multiplication, blank times 4 can be interpreted as some number of groups of size 4 equals 20. So that's going to give us a different interpretation, right? Because previously we knew the number of parts, but we did not know the size of each part. And now it's exactly the opposite. We don't know the number of parts, but we do know the size of each part. Each part has size 4. We could draw this in a diagram by again having the whole bar represent 20, one part of it represent 4, and then this kind of ... question mark illustrates that the question mark is how many of these 4s fit into 20. So if we were trying to just use language to interpret this diagram, we might say 20 is how many 4s, or how many 4s make up 20. It's a different interpretation than the partitive interpretation. So again, just like with subtraction, there are two kind of fundamentally different ways in which real-world situations reduce down to division. Again, before we move on, we call this measurement division. One reason why we could do that, or one way we could remember that, is that in this interpretation, we know the measure of each part. We know the measure or the size of each part. That's measurement division. If we happen to know the number of parts, that would be partitive division. Again, like the interpretations of subtraction, it's not necessary that students know the words partitive and measurement, but what they need to see is that both of these interpretations reduce down to division. Oftentimes, we might focus on one interpretation over the other, but we want students to get a mixture of word problems that use both interpretations, so they're comfortable, that is, reducing both types of problems down to the same operation. Now, one of the main reasons we focus so much on partitive and measurement division is that this understanding of how partitive and measurement division works for whole numbers can really pay dividends when it comes time to discuss division of fractions. Now, we'll talk about division of fractions much more in a later clip, but what I want to do here, since we're talking about partitive and measurement, is just talk about how partitive and measurement can be applied to consider a fraction division problem. So instead of 20 divided by 4, let's just replace the 20 and the 4, the dividend and the divisor, with fractions. So for example, what if we used instead of 20 and 4, 7/4 and 2/3. Right? So let's now consider the fraction problem 7/4 divided by 2/3. Oftentimes when students see something like this, they just automatically assume they can't do it, that it's too hard for them to solve. They just don't, fraction division is a very kind of hard concept to understand at the elementary school level. But if it's taught in the context of partitive and measurement division, then we can draw back on what we know about division of whole numbers, and we can apply that to how division works with fractions. Okay, we always want to do that whenever possible. We want to take a concept and we want to relate it back to something that we already know how to do. Everything is connected, and we really want to show that to our students. Okay, so suppose we have 7/4 divided by 2/3. Again, we have the same idea as before. The answer to this question is the number that multiplies by 2/3 to give us 7/4. But we know that we can do this in two ways, right? We have the commutative property of multiplication that tells us blank times 2/3 equals 7/4 is equivalent to 2/3 times blank equals 7/4. So how could we draw diagrams and interpret these situations like we interpreted the 20 divided by 4 example? I am going to leave up not the diagrams, because in one case they're going to look different, but I'm going to leave up the old questions, what we might call an interpretative question for, let's leave up the original problem actually. So we had 20 divided by 4 equals blank in both cases. Just to remind you of how these questions are interpreted from a partitive and measurement standpoint. So again, what we talked about a couple of minutes ago, from a partitive perspective, 20 divided by 4 equals blank is equivalent to the question, 20 is 4 of what? Or 20 is 4 of what number? Okay? So now all I'm going to do is I'm going to replace wherever I see a 20, 20 was the dividend in my previous problem, and 7/4 is the dividend in my new problem. So all I'm going to do is I'm going to replace 20 with 7/4, and I'm going to replace my old divisor of 4 with my new divisor 2/3. So my new problem again is 7/4 divided by 2/3. I'm going to do the same thing in this interpretative question. So instead of the question reading 20 is 4 of what, now it's going to read 7/4 is 2/3 of what? Again, the interpretation is exactly the same. It shouldn't matter what types of numbers or what numbers I'm plugging in for the dividend and the divisor. The interpretation is going to be exactly the same if I'm staying consistent with a partitive interpretation. With whole numbers, it was 20 is 4 of what? With fractions, it's 7/4 is 2/3 of what? Now that I understand that this is the interpretative question, can I draw a diagram that reflects this situation? Drawing diagrams is going to be really important when we talk about fraction division in general, and especially when we come to solve word problems that involve fraction division. And again, keep in mind we will talk about fractions in great detail in later clips. But I think even if we don't know that much about fractions, we could still draw a picture that illustrates this situation. 7/4 is 2/3 of what? Well, the what is going to be our entire bar. We want 2/3 of this bar. So we can cut our bar into 3 pieces and shade 2 of them. This is just very basic fraction knowledge. And the 2/3 of the entire bar, that's what 7/4 is equal to. Because once again, the question reads 7/4 is 2/3 of what? So notice that we have a pretty good understanding of the division problem 7/4 divided by 2/3, which on the surface looks like a pretty intimidating problem, just purely by resorting back to what we knew about division of whole numbers from a partitive perspective. All I did was take my old information and just replace that with these new numbers 7/4 and 2/3. Okay? And we'll certainly return to problems like this later on. We can do the same thing from a measurement perspective. From a measurement perspective, remember the original 20 divided by 4 problem. Now the role of the divisor changes. Instead of the divisor representing the number of parts as it did with partitive division, now the divisor represents the size or the measure of each part. So the interpretative question we have with measurement division is 20 is how many 4s? Okay? Now I'm going to do exactly what I did last in our partitive example. I'm just going to replace the 20 and the 4 with 7/4 and 2/3, my new dividend and divisor. 7/4 is my new dividend, 2/3 is my new divisor. So the question will now read, 7/4 is how many 2/3? And as we did with the partitive example, now, again, we don't need to know a lot about fractions to be able to draw this picture. In fact, this picture is going to look exactly the same as the measurement division picture involving whole numbers. We can't quite say the same thing for partitive division, but we can say this for measurement division. 7/4 is how many 2/3? We would draw this by labeling the entire bar 7/4. One piece of it is going to be 2/3, and the answer to the question, again, is how many 2/3 make 7/4, right? So again, partitive and measurement interpretations are very, very powerful. Simply by understanding what a bar diagram would look like, what an interpretive question would look like, we can not only get information about whole number division, but fraction division as well. And fraction division, again, is one of the more difficult topics in the entire elementary school curriculum. Okay, so the next thing I want to talk, so the last thing I want to talk about is division by 0, which is one of the biggest sources, I should say, of misunderstanding that I've ever seen at the elementary level, okay? This is probably because this topic is not treated in a lot of elementary school textbooks. But it seems like it should be, because what ends up happening if it's not treated is students will come to their own conclusions about problems like this. These conclusions will not be corrected, and they will carry these misunderstandings with them to high school and college. So, for example, if this topic wasn't treated, how would a student interpret a problem like 6 divided by 0? Think of all of the other multiplication and division problems that involve 0. So we might have 0 times 6, we might have 6 times 0, and we might have 0 divided by 6. Now, the answer to each of these first 3 problems is 0. 0, as we talked about as we saw when we discussed multiplication, 0 multiplied by any number is 0. So 0 times 6 is certainly 0, and 6 times 0 is certainly 0. 0 divided by 6 is 0 as well. And this is simply due to the definition of division as the inverse of multiplication. So a student who is not taught or explained how 6 divided by 0 needs to be interpreted is probably going to think, well, all the answers to all these other problems is 0. The answer to this problem must be 0 as well. And we see many, many students who come up through the college level that still think that division by 0 returns 0. Okay? And the reason why this is a very rich topic is that it kind of underscores our whole thought process as we teach at the elementary level. Okay, we want to teach for understanding. We want to teach based on precise definitions. And all it takes to completely understand 6 divided by 0 is a 1-minute explanation that involves the definition of division. So let's start the clock in a minute. Now, if we recall the definition of division, 6 divided by 0 equals blank is equivalent or means the exact same thing as blank times 0 equals 6. And this is all that it takes to correctly explain that 6 divided by 0 cannot be 0, right? Because 0 does not go into this blank. 0 times 0 is not equal to 6. In fact, no number goes into this blank, right? Because anytime you multiply by 0, it returns 0. It never is going to return 6, right? No number goes here. But again, division is the inverse of multiplication. These number sentences mean the exact same thing. Remember back to our 20 divided by 4 example. If 20 divided by 4 equals blank, that's the number that multiplies by 4 to get you 20. If 6 divided by 0 is blank, the blank is the number that multiplies by 0 to get you 6. There is no number that multiplies by 0 to get you 6. Therefore, there is no number that satisfies 6 divided by 0. Okay? So for that reason, we say 6 divided by 0 is undefined. Again, this might be perhaps why elementary school teachers shy away from this type of discussion, is that maybe undefined is too complicated of a concept to get across to elementary school students. However, the alternative in many cases is students mistakenly thinking that the answer to 6 divided by 0 is 0. And that's going to cause huge problems when they get to high school and college, because there are many, many situations in which division by 0, quote unquote, happens. And if they think that the answer is always 0, then they're going to misunderstand a great many concepts going forward. Okay? One last issue you might be thinking of, well, 6 divided by 0, you might be able to see pretty quickly why nothing fits in this blank. But what if I replace the 6 with a 0? What about 0 divided by 0? So again, using our definition of division, 0 divided by 0 equals blank means blank times 0 equals 0. And now we kind of have the opposite problem. Instead of no number fitting in this blank, every single number fits in this blank, right? Anything you could put in here is going to satisfy this last equation, right? All numbers go here. This is a problem. We just talked about the so-called quotient remainder theorem, right? And when we divide two numbers, the quotient and the remainder are unique, meaning there's only one answer if we restrict the remainder to being less than the divisor and non-negative. So in all division problems, we need the quotient and the remainder to be unique. But in this division problem, they are not. The quotient could be anything if we go by our definition of division. Okay, so for that reason, we are also going to say that 0 divided by 0 is undefined. Because how would you define it? Every single number could go in that blank. We don't want to say that every single number could be the answer to this question. So for a slightly different reason, we're also going to say that 0 divided by 0 is undefined as well.